All right, this is the final lesson in Unit 9. This is a long lesson. It's called Graphing Rational Functions. Okay, so the first 6 pages, we're going to go over one topic per page. Okay, I have 6 different topics we're going to talk about, and the final 2 pages is bringing them all together to graphing. Okay, so recall that a rational function is any function which can be defined by a rational fraction. Okay. For example, an algebraic fraction such that both the numerator and the denominator are polynomials. Okay. So the first page is going to be about finding the domain of a rational function. So finding what x values you can have in a rational function. Okay. So step 1, a rational function is simply a fraction. In a fraction, the denominator cannot equal 0 because it would be undefined. Okay. To find which numbers make the fraction undefined, create an equation where the denominator is not equal to 0. Step 2, solve the equation found in step 1. And step 3, write your answer using interval notation. That's what we've done all year long. Okay. So, step 1, create an equation where the denominator is not equal to 0. So in example 1, the denominator cannot be equal to 0. So 1a, x plus 8 cannot equal 0. That's step 1. Step 2, solve the equation found in step 1. Okay, so solve that equation. X cannot equal negative 8. Step 3, write your answer using interval notation. So that's the notation we've used all year long, okay? So in other words, the domain can be everything except negative 8, meaning the domain goes from negative infinity up to negative 8, union, and then it goes from negative 8 up to infinity. Since I have the parentheses next to the negative 8, it means it's not included in the answer. Okay, so this is the domain, everything except negative 8. Example 1b is a little more difficult. Okay, we're going to follow the same 3 steps above. Step 1, create an equation where the denominator is not equal to 0. Now we have to solve that. Okay, so what we're going to do is we're going to factor. Find 2 numbers that multiply to negative 24 and add to negative 5. Okay. So it'll be negative 8 and positive 3. After you factor, set each factor equal or not equal to 0 and solve. Okay, x minus 8 cannot equal 0, and x plus 3 cannot equal 0. So x cannot be 8, and x cannot be negative 3. Here's my domain. I'm going to write it in interval notation. The domain goes from negative infinity up to negative 3. But it's not including negative 3, so I'm going to put a parenthesis next to it. Then the domain goes from this point up to 8, not including 8, and not including negative 3. So negative 3, parenthesis 8, both in parentheses because they're not included in the domain. And then the domain continues from 8 up to infinity, but not including 8, so I put a parenthesis next to the number 8. This is the domain. Okay. Domain is the x values in the graph. The next page talks about finding the x-intercepts, okay? So here are the 3 steps. Step 1, factor if necessary. Eliminate the common factors. Now that is key. Step 2, set the numerator equal to 0 and solve. And step 3, write your answer in the form x comma 0, because that's how you write an x-intercept properly. Okay, so here we go. I have 2 examples, 2a and 2b. Okay, step 1 says factor and eliminate the common factors. So f of x equals, factor out the GCF from the numerator. The GCF is 4. So you factor out the GCF of 4 and it leaves you with x minus 5. Okay. Eliminate the common factors if there are any. In this one, there are no common factors, so there's nothing to eliminate. Okay. Now remember, for the x-intercepts, you're going to set the numerator equal to 0 and solve. Okay. If the numerator is 0, then this whole thing is 0. So you're going to set the numerator equal to 0 and solve. 4 times x minus 5 equals 0. So either 4 equals 0, which you can ignore, or x minus 5 equals 0, which gives you x equals 5. That is your x-intercept. So we're going to write it in the proper way, parenthesis x comma y. The x-intercept equals 5 comma 0. And again, the reason why we set the numerator equal to 0 is because if the numerator is 0, then the fraction is 0 over any number, which means it's 0. So it means that f of x or y is 0. Okay, 2b, we're going to follow the same 3 steps. Step 1 says factor if necessary. So we're going to factor the numerator first. Find 2 numbers that multiply to negative 12 and add to negative 1. So it'll be x plus 3 times x minus 4. The denominator has a GCF of 2. So we'll factor out the GCF of 2. It'll leave you with x squared minus 2x minus 8. Now what you're going to do is you're going to factor the denominator again. Factor the parentheses in the denominator. Find 2 numbers that multiply to negative 8 and add to negative 2. So it'll be x plus 2 times x minus 2. I mean x plus 2 times x minus 4. Now you have to be careful, okay? Because it says above, step 1 says factor if necessary, and it says eliminate the common factors. That is important that you eliminate it. We'll talk about that more later. But you must eliminate the common factor of x minus 4. If there are common factors, eliminate them. Example 2a, there were none. This one does have a common factor of x minus 4, so you divide that out, and you're left with f of x equals x plus 3 over 2 times x plus 2. Step 2 above says set the numerator equal to 0 and solve. So x plus 3 equals 0. X equals negative 3. So that's the x-intercept, okay? So the x-intercept equals negative 3 comma 0. Okay, the next page talks about y-intercepts. Okay, remember, for any y-intercept, x equals 0. So step 1, set x equal to 0 and solve. And then step 2, write your answer in the form parentheses 0, comma y. Okay, so set x equal to 0 and solve. So I'm going to have 0 squared plus 7 times 0 plus 10 over 0 minus 5. So in the numerator, that's 0 plus 0 plus 10. Still got 0 minus 5 in the denominator. Simplify the numerator to get 10. Simplify the denominator to get negative 5. 10 over negative 5 equals negative 2. So the y-intercept is negative 2. You can write it in the form 0, comma y. Okay, so the y-intercept equals 0, negative 2. Okay. One more, example 3b. Again, set x equal to 0. So negative 3 times 0 squared plus 2 times 0 minus 9. All divided by 0 to the 5th power minus 3. Okay, let's clean up the numerator. 0 squared is 0 times negative 3 is still 0. Plus 2 times 0 is 0, minus 9. 0 to the 5th power means 0 times 0 times 0 times 0 times 0. That's still 0. And then minus 3. That gives us negative 9 over negative 3, which equals 3. The y-intercept equals 0, comma 3. Here. 3 pages down, 5 pages left. Unfortunately, I think those are the 3 easiest pages. Okay, the next page talks about finding holes of a rational function. Okay? A hole exists on the graph of a rational function at any input value that causes both the numerator and denominator of the function to be equal to 0. Holes are also known as removable discontinuities. Okay? So the key part is it causes both the numerator and denominator to be 0. Okay? So here's what we're going to do. Example 4, state the holes of each rational function. You're going to start by factoring. Okay, if possible, let's factor. So we're going to factor the numerator here because you can factor the numerator. Find two numbers and multiply to 10 and add to 7. X plus 5 times x plus 2, divided by x plus 2. Now what you do is you divide out the common factor. You get f of x equals x plus 5. I'm just going to jot down what I'm doing. I factored and I simplified. Now, we have a hole that's associated with these two expressions that or factors that you canceled out or divided out, okay? So what we do to find the hole is we take our common factor that we divided out and we set it equal to 0, okay? So I take the common factor that I divided out and I do x plus 2 equals 0. That gives me x equals negative 2. That's my hole. So let me just jot down what I did there so you can see. I said, let's say set common factor equal to 0. Okay, so that's the x value of the whole. Now we have to find the y value of the whole. Okay, and you get that by taking this and substituting it into the new function. By new function, I mean this right here, after we simplified. Okay, so let's say f of x equals x plus 5. Substitute the x value into that function. So negative 2 plus 5 equals 3. So I'm just going to say substitute into new function. Not the original function, the new one. Okay. So we have the final answer. We have a whole at negative 2, comma 3. Here we go, one more like that. Again, since this one's kind of hard, this page, I'm going to explain what I'm doing in each step. Okay, first we're going to factor and simplify. So factor the numerator, if possible, and factor the denominator, if possible. To factor the numerator, find two numbers that multiply to negative 6 and add to 1. X plus 3 times x minus 2. To factor the denominator, that's the difference of two squares. A squared minus b squared equals a plus b times a minus b. So it'll be x plus 2 times x minus 2. Divide out the common factor of x minus 2. It gives you x plus 3 over x plus 2. So again, let me explain what I'm doing in each step because this is hard. Factor and simplify. That's what I did. Now set the common factor equal to 0 to find the whole. So the common factor that we divided out was x minus 2. So I'm going to do x minus 2 equals 0, which gives me x equals 2. So I'll say set common factor equal to 0 again. So that's the x value of the whole. Now we have to find the y value of the whole. So we're going to substitute into our new function. The new function is kind of messy still, x plus 3 over x plus 2, remember? Again, I'm going to jot down what I'm doing, substitute into new function. And you replace the x, if you recall, with the x value from the step above. So 2 plus 3 over 2 plus 2. That's going to equal 5/4. 5 over 4. So it's a fraction, that's okay. Okay, 5 over 4. So the final answer. And again, you can have more than one whole. But our whole is at x, comma y. 2, comma 5/4. Okay. The next page is on vertical asymptotes. We talked about asymptotes early in the year when we did logarithms and exponentials. Okay. An asymptote is a line that the graph of a function approaches but never touches. To find a vertical asymptote, you are trying to find values of x that produce 0 in the denominator, but not in the numerator, because that would be a hole. Okay? If 0 over 0 occurs, that means you have a hole in the graph. There we go. Okay. Step 1, factor if necessary, eliminate the common factors. And step 2, set the denominator equal to 0 and solve. Before we move on, just to refresh your memory, this is a vertical asymptote. And it's always x equals a number because it's a vertical line. So let me just jot down x equals 1 is a vertical asymptote. Example 5a, state the vertical asymptotes. So step 1 above said factor if necessary, eliminate the common factors. Okay, so the numerator is fine. We have to factor the denominator, find two numbers that multiply to negative 16 and add to negative 6. It'll be x plus 2 times x minus 8. Okay, step 1, factor if necessary, eliminate the common factors. We have no common factors, so there's nothing to eliminate. Okay. Step 2, set the denominator equal to 0 and solve. X plus 2. Solve each one. Either x plus 2 equals 0, which means x equals negative 2, or x minus 8 equals 0, which means x equals 8. So those are the vertical asymptotes, okay? These are my two vertical asymptotes. These are basically what x cannot be, remember? Because the denominator cannot be 0. So it's kind of like the domain problems, but you do have to be careful, okay? So the vertical asymptotes are going to be x equals negative 2 and x equals 8. Okay, example 5b again. Step 1 above says factor if necessary, eliminate the common factors. So factoring the numerator that has a GCF of 3. So you factor out the 3, leaves you with x squared minus 4x minus 5. To factor the denominator, find two numbers that multiply to negative 10 and add to negative 3. So it'll be x plus 2 times x minus 5. Now you have to factor the numerator again because it can still be factored, okay? So in the parentheses, find two numbers that multiply to negative 5 and add to negative 4. Multiply to negative 5, add to negative 4. So it'll be x minus 5 times x plus 1. Now, you have to be careful, okay? Because it says step 1, factor if necessary. Eliminate the common factors. You have to eliminate the common factor, okay? You're not going to do anything with the x minus 5 that does not have an asymptote there. That's where the hole is. Remember back to the last page, the hole? There's a hole at x equals 5, okay? So we don't care about that for now, okay? So what do I have left? I have 3 times x plus 1 in my numerator. My denominator is just x plus 2. Okay. Set the denominator equal to 0 and solve. So x plus 2 equals 0. X equals negative 2. That is my vertical asymptote. Okay. You could have 1. You could have more than 1. This one just has 1. And again, you write it as x equals because it's a line. X equals. One more topic before we move on to the actual graphs, which is basically going to be combining everything. Okay. The next page, so that page was vertical asymptotes. The next page is about horizontal asymptotes. An asymptote is a line that the graph of a function approaches but never touches. So in this diagram, y equals 2 is a horizontal asymptote. Okay, remember, it's y equals a number because it's a horizontal line. Y equals 2 is a horizontal asymptote. Okay. There are 3 scenarios to find out what the horizontal asymptote is. Okay, and then I have one example with 3 parts, so it's going to be one of each. Okay, so here are the 3 scenarios. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Okay? That's the first scenario. The second scenario, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. Okay? That's the second scenario. And the final scenario, if the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, so we're going to do one example on each. Okay, example 6, state the horizontal asymptotes of each rational function. So 6a, the degree of the numerator equals 2. And the degree of the denominator equals 1. And we talked about degree earlier in the year, the highest exponent. Okay. So which scenario is it above? It's the top one. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. So let's jot that down. Say no horizontal asymptote. Part B, the degree of the numerator equals 1, the degree of the denominator equals 2. Degree of numerator equals 1. Remember, if you have just one variable, then it's whatever the highest exponent is. Make sure it's in standard form, though, to help you see it better. So, which scenario is it above? It's the second one. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. Y equals 0. Part C, the degree of the numerator equals 2, the degree of the denominator equals 2. Again, you really want to make sure it's in standard form. Okay. So, which scenario is that? It's the third one. Okay. If the degree of the numerator is equal to the degree of the denominator, then the horizontal asymptote is y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay. So leading coefficient is a number in the beginning when it's in standard form. So the leading coefficient of the numerator is 3. And the leading coefficient of the denominator is 1 because it's 1x squared because there's no number in the beginning. So 3 over 1, which is just 3. So horizontal asymptote is y equals 3. Okay. Now what we're going to do is we're going to bring everything together, and we have 2 examples where we're going to graph rational functions. Example 7 and example 8. All right, here we go. So basically what I'm going to do is I'm going to run through each of these topics that we did earlier. This problem asks for all of these, so let's go one at a time. Let's start with the x-intercepts. Could be more than one. Okay, so the x-intercepts, that was back on the first, actually the second page. Factor if necessary, eliminate the common factors, set the numerator equal to 0 and solve. Okay, so there are no common factors. There's nothing to factor. So I'm going to set the numerator equal to 0 and solve. 2x plus 5 equals 0. X equals, subtract 5 divided by 2. X equals negative 5 halves. So I'll say negative 2.5. So I'm going to write that as negative 2.5 comma 0. That's the x-intercept. Let's graph it as we go. For the y-intercept, that's when you replace the x with 0. Let's do that over here. So going back to the original problem, 2 times 0 plus 5 over 0 minus 1. Five over negative 1. Equals negative 5, so the y-intercept will be 0, negative 5. Label that right here. And let's graph that. That way we don't forget. Let's do the holes next. Now, again, this one has no common factors. So that means there's no holes. The next one will have a hole. Okay? No common factors. That means there's no holes. So I'll say none. Next up, let's do the vertical asymptotes. Okay, so we did that earlier in the lesson. Okay, the steps for the vertical asymptotes would be factor if necessary. This one, there's nothing to factor. Eliminate the common factors. There are no common factors. So set the denominator equal to 0 and solve. Okay, so the denominator is x minus 1, remember. Get x equals 1. Now, let's graph that. Now, the graph never touches the vertical asymptote. So what I'm going to do is I'm going to go to x equals 1. I'm going to put a dashed line. It's not actually part of the graph, but I'm just going to put a dashed line at x equals 1. Now let's do the horizontal asymptote. That was the page right before this, okay? The degree of the numerator equals 1, and the degree of the denominator equals 1. So it means the asymptote, the horizontal asymptote, is y equals leading coefficient of the numerator, which is 2, divided by leading coefficient of the denominator, which is 1, because it's 1x. Y equals 2 over 1, which is y equals 2. Let's do a horizontal line at y equals 2. Dashed 1. That way you know the graph never intersects there. Now we're going to need some additional points, okay, because this is not good enough. Okay. So I'm going to do a bunch of additional points. I'm going to start with x equals 8. Let's start with x equals 8. So going back in the original problem, that's 2 times 8 plus 5 over 8 minus 1. So it'll be 16 plus 5 is 21 over 7. Equals 3. That means we have the additional point 8 comma 3. I don't like those equal to symbols. I'm going to get rid of that. Okay. So what we should do now is let's graph that as we go. Let's graph the additional points as we go. Let's graph 8 comma 3. Let's do some more additional points. I'm going to go with x equals negative 6. Want to be smart with how you pick these. Don't pick anything on an asymptote, of course. Let's do x equals negative 6. So 2 times negative 6 plus 5 from the original problem over negative 6 minus 1. So that's negative 12 plus 5 equals negative 7 over negative 7, which equals 1. So we have the additional point, negative 6 comma 1. Graph that. Let me get a couple more. I'm going to go with, let's do x equals 2. Go back in the original problem. 2 times 2 plus 5 over 2 minus 1. That'll be 9 over 1 equals 9. That means you have the additional point, 2 comma 9. Graph that. And you know what? I'm going to do one more. Let's do x equals 4. Let's do it again. X equals 4. Okay, so go back in the original problem, 2 times 4 plus 5 over 4 minus 1 will be 13 over 3, which is approximately 4.3. Means you have the point 4 comma 4.3. So we can just estimate that. Just estimate that. 4, 1, 2, 3, 4, go a little past 4, like that. And now you'll see like the basic shape for these graphs. And again, the asymptotes could be reversed, or the graphs could be in the opposite quadrants than we have here. So now we're going to touch the asymptote, remember. This one. It does not touch the asymptote. Something like that, maybe. That looks good. Okay, one more. I'll go a little faster through this one. This one is a little harder, though. Graph this. Okay, so let's go in order. Let's find the x-intercepts first. So we're going to factor and divide out the common factor, okay, for the x-intercepts. Factor the numerator. The numerator has a GCF of 2x. Leaves you with x plus 3 in parentheses. Factor the denominator. Find two numbers that multiply to 3 and add to 4. X plus 3 times x plus 1. Divide out the common factors, if there are any. And then what you do, if you remember back to, I believe, the second page, set the numerator equal to 0 and solve. So 2x equals 0, x equals 0. That means your x-intercept is 0, comma 0. By the way, that means the y-intercept is also 0, 0. Or maybe there's more than one. Let's do that next. And graph it as you go. So plot it as you go. To find the y-intercepts, remember you replace all the x's with zeros. Okay. So going back in the original problem, it's 2 times x squared, so 2 times 0 squared, plus 6 times x, so plus 6 times 0, divided by x squared, so 0 squared, plus 4 times x, so plus 4 times 0, and then plus 3. So look what that gives you. That gives you 0 squared is 0, times 2 is 0, plus 6 times 0 will be 0 plus 0 over 0 plus 0 plus 3. So that's 0 over 3, which is just 0. So that means the y-intercept is 0, comma 0. And that's it. Okay. So 0, comma 0. Okay. Now it's time to do the holes. So let's do the holes now. You take your common fact that you divided out and you set it equal to 0. So way back, the common factor that we divided out was x plus 3. You know what I'm going to do? I'm just going to recopy that, just to help us see it better. So we divide out the common factor of x plus 3. And now what we do is we set that equal to 0. So we do x plus 3 equals 0. That'll give you x equals negative 3. this in a little bubble to help us see it better. And then what I do is I take that -3 and I substitute it into my new function. So my new function is this: f of x equals 2x over x plus 1. And I replace the x with -3. So here's what I have. 2 times -3. The reason why I'm using -3 is because that's the x value of my whole. Over -3 plus 1. So it'll be -6 over -2, which equals 3. So the whole is at -3 above, comma, 3. So what I do is I'm going to write that right here. And let's plot that, okay? Where it's a whole. It's a whole. Vertical asymptote time. So again, I'll just recopy everything. Here's the factored form. Okay. After we divide out the common factors, what we do, if you remember, you take your denominator, whatever's left over, in this case x plus 1, do x plus 1 equals 0. That'll give you x equals -1. So that's the vertical asymptote. Graph it. Vertical line, put a dash, put it dashed. Horizontal asymptotes. The degree of the numerator equals 2. The degree of the denominator equals 2. That means the asymptote is going to be y equals 2 over 1. Leading coefficient of the numerator divided by leading coefficient of the denominator, which is 2 divided by 1. So y equals 2. Graph that, horizontal line at 2. And now we have our asymptotes graphed, which is great. Let's just get a few additional points and let's end it. Okay. You'll notice how these are in the different quadrants from last time, the last example. Okay, so let's do 2 additional points, then we'll call it a day. Let's start by doing x equals 1. You want your graph to look nice. Then I'll do x equals -2. And you want to like spread it out. So I'm gonna get one more additional point in each of these quadrants, and then that'll be it. For x equals 1, we're going to substitute back into the original problem. So it was 2 times x squared, so 2 times 1 squared, plus 6 times x, so plus 6 times 1, over x squared, so 1 squared, plus 4 times x, so plus 4 times 1, plus 3. So numerator will be order of operations. 1 squared is 1, times 2 is 2, 2 plus 6. The denominator will be 1 plus 4 plus 3. Eight over 8, which equals 1. So my additional point is going to be 1, comma 1. Let's graph that. My other additional point, let's do x equals -2, I said. So it's going to be 2 times x squared, so 2 times negative 2 squared, plus 6 times x, so plus 6 times negative 2, over x squared, so negative 2 squared, plus 4 times x, 4 times negative 2, plus 3. Okay? So you got to be careful for the order of operations. Negative 2 squared is 4 times 2 is 8. And 8 plus negative 12. The numerator will be 4 minus 8 plus 3. So the numerator will be negative 4. The denominator will be negative 1, so that equals 4. So we have the additional point, negative 2 comma 4. Graph that. And now I got my 2 points on each side, okay? I have my asymptotes. I'm just going to go and graph it. You've done enough, okay? If you watched this entire video, then shout out to you. I'm impressed. If you did watch it, hopefully you took a break in the middle because this is long. It should look like that. And that is the end of this lesson, graphing rational functions.